I just want to thank you for sticking out through the second day of talks and acknowledge my co-authors. Stephanie at our station did a lot of the lab work. Our partners with DEC, Scott Cornett, Pete Osterman, and Fred Hansen, who who took all the samples, as well as Betsy Trometer and Tom Hoffman from our Great Lakes office, who also did a lot of sample collection and provided the funding. So this is it's a definitely a collaborative project, and we appreciate all the support from the partners on that. In addition to Scott's offer to pinch hit in case I had to drive home if we shut down. So he can give this talk anytime. He's all ready to go. So the objectives of our project were twofold primarily. First, really assess patterns of genetic diversity among brook trout populations in western New York. Where we were covering 4 different watersheds. We also wanted to examine the genetic influence of potential remnant effects of previous stocking efforts that had occurred in some of those tributaries. Our samples, we had about 50 different sample sites collected over 4 different watersheds, including the Randolph State Hatchery stream. We had about just over 2,000 samples, and we have actually another 2,000 samples that we'll be adding to this data set this spring, which includes primarily samples from the Susquehanna, Allegheny, and Genesee. So we're really going to be boosting up our sample size, basically doubling the number of sites that are represented, hopefully, for the next talk. You can see here, these are the 4 watersheds that we were focusing on, all these different sites represented where we, all the dots represent different sites where we had samples collected from. As you can see, the Susquehanna isn't really well represented yet, but it will be soon. So our methods were very similar to what we just presented. So we looked at characterized microsatellite loci for all the different populations. We also looked for identity testing within the samples to identify any duplicates, which we did find a couple individuals that have been resampled, and I'll talk about those a little later. We characterized all the data, basically looking at different estimates of diversity to look at how that diversity was partitioned both within the site and across sites using a variety of different analyses. So I just wanted to highlight, rather than looking at all 50 data points on the slide, just some of the sites that have the lowest diversity and some of the sites that have the highest diversity. So for the next few tables, you'll see this is our sample size per site. This is the number of alleles per locus that, for each of the different sites, and then also the allelic richness value, which basically just standardizes that allelic diversity as a function of the sample size. We had some sites that were a little bit lower. So here we had a site that had just 30. Most of the sample sizes were closer to 50, although we had a little bit of variation. These are our estimates of heterozygosity, expected and observed, and then our inbreeding estimates. We're back. So I just wanted to point out a couple things. So some of these lower diversity populations, our allelic diversity values are pretty low. So on average, looking at 2 to 3 alleles per locus, which is showing that across all 12 loci, we don't have a lot of diversity in some of these populations. Working with Scott and Pete and Betsy and Tom, talking about some of the sites where we found these diversity estimates. A lot of these sites were very small populations, maybe had a history of going through bottlenecks, and so as you expect over time, those diversity estimates in a population that maybe was higher and maybe a larger population initially, over time those have become depressed due to either habitat conditions or population fluctuations. In some of these higher diversity populations, so we have 4 sites that have estimates of allelic diversity that are closer to between 7 and 8 alleles per locus. Those, looking just at this allelic gain metric, those are more consistent when we look at estimates of diversity for populations of brook trout in Pennsylvania that are coming from really good population numbers with well-connected habitat, really good kind of reference sites that you would expect brook trout to be in. So some of these sites have really good diversity estimates, but of all 50 sites, we only have 4 of those that have those higher diversity estimates. Pretty quickly, we already have a population in our high category that's already known to 5 alleles per locus. So some of these, especially talking with biologists, a lot of these sites are kind of on the edge, potentially, in terms of habitat standpoint. or competitive effects with brown trout. So if we want to kind of dial in a little bit, looking at some of these sites, so we've got our lowest diversity populations. They're kind of scattered all over the map. So we have a few from Allegheny, one from the Genesee. They're also, they have, a lot of them have brook trout populations that are nearby. So potentially they have connectivity issues. Maybe they're isolated potentially from some of those nearby populations, either through some sort of either physical barrier or maybe even a temperature barrier that's preventing migration. And if we look at these high diversity sites, they're also intermixed in amongst some of these other sites. So we have some low diversity sites here on Allegheny in the red, but here at green, just nearby, we have a high diversity site. So potentially if you're looking at trying to restore connectivity, potentially that might be an area to focus on with maybe some passage or habitat improvement efforts. If we were to look at another metric of within population diversity or understanding a little bit about how that population is structured is looking at estimates of effective population size. These metrics kind of give you an estimate on the number of breeders in a given year that are successfully contributing offspring to subsequent generations. It's an estimate of thinking about how many individuals are necessary in a population to be reproducing and result in the same estimates of diversity in subsequent generations. Rather than looking at all 50 sites, just highlighting a few of the results here. So some of these 3 sites have the lowest effective population size. These are really, really low estimates. So Craig Creek has an effective population size of 3.8 individuals. And then if we look at some of our high effective population size estimates, these are more consistent with what you would expect. They're still low. If you think about some of the genetic diversity literature and what you expect for maintaining diversity in a population long term. But if we apply these to brook trout populations that we've been monitoring over time, where we know there's good quality habitat and really connected populations with gene flow, they still actually commonly have these, high, what they're considered high for brook trout, but still relatively lower estimates of effective population size. What this means is potentially those populations have gone through genetic bottlenecks over time. So populations might have been larger initially and have gone through numerous activities that might have constrained populations. We'd also be expecting that a lot of these individuals are probably related, and that maybe can be downward biasing those estimates of effective population size. So here I just have a couple points about things that can cause those effective population size estimates to really reduce, or could be biasing those estimates. However, I think even with some of these occurring, those sites probably have actually really low estimates of effective population size. Another thing we can look at is estimates of among population diversity and kind of thinking about how these populations cluster across the landscape. Are they more similar to each other? Kind of close by or within the watershed. And so we can look at that in a variety of different ways. Excuse me. This is a principal component analysis plot of FST values, so looking at allelic differences between each individual site on a pairwise manner. And we can see that, probably not from the back of the room, sorry, this font's really small, but all these little orange dots, these are all Allegheny watershed sites. And you can see most of them are kind of clustered here, but we do see a few scattered throughout the graph. The Genesee sites all pretty much clustered together. We have a couple that are scattered a little bit farther, not quite as distributed as the Allegheny sites. A couple that, of course, we didn't have very many sites from Erie, but we had a few. There's a few here in the middle. There's a couple here and down here. I'll talk about this site here in a little bit. And we just had a couple from Susquehanna at this point, but we'll be, like I said, mentioning really increasing those sample size. So this is saying we get some clustering, some grouping by the watersheds across our sites. Another way to look at it is looking at, on an individual population level, doing an assignment test. So of all the sites, basically taking an individual out of its population, assigning it back to, and then asking which population is this individual most genetically similar to. And across the board, on average, 94% of those individuals of all the individuals assigned back to their population of origin. So this is demonstrating that there's a lot of genetic differentiation between the populations, and they're all relatively genetically unique, and those individuals could be assigned back to that population of origin. If you took them out and lost the sample and didn't know which population this belonged to, you, for the most part, be able to tell exactly which population it came from. We saw these structure plots in the previous lab presentation, and so I'm showing them again here. It's just a way to look at, without any sort of a priori knowledge, how do those populations, of a set of populations that you might be considering, what does the genetic information say about how many populations or groups might be actually present in that sample? So here we have actually 15 sites, and each of the different colors represent kind of a different genetic group. And of the optimal K value that we found for, this is the Genesee, we've actually found 14 groups within the 15 sites that we looked at. These two sites here grouped together, and then these two sites here grouped together. So we had a grouping down here and a grouping down here among those sites. It's not saying there's probably gene flow between those two locations. And if you look on the map, they're pretty geographically close to each other. When we look at, in terms of this Randolph Creek hatchery strain, which was stocked in some of these locations, we see a few individuals that might have some signatures of introgression, and that's something that we're going to be looking at a little bit more. There were two sites that had a little bit of introgression that looked like Ainsworth Creek, or Ainsworth Brook and Benmore Creek. If we look at the Erie drainage, again we had 7 sites, including if we included the Randolph hatchery strain. There was a high K value, meaning a high out of the potential number of sites. There were also a very similar number of groups. We had 6 groups. It actually clustered this one site here, very similar to the Randolph Creek strain, which we don't necessarily think is due to introgression. As we saw on that scatter plot, that was the site that was very close in that graphic next to the Randolph Creek strain. Potentially this is just a function of isolation of that population over time, and the random process of genetic drift has resulted in allele frequencies that might be similar to that Randolph Creek strain. But that's something we're going to look at a little bit more. So yeah, so right here, this was that site here that was pretty close to the Randolph Creek strain. Right here. If we look at the Allegheny, we had 28 sites, and there were 25 groups that were identified. Most of these sites were again unique. We had a couple sites here that were grouped together here and here. You can see these two sites, and those are geographically very close to each other. So there's likely some gene flow occurring, which would lead to that similar kind of genetic signature between those two sites. I'm going to focus in on this little group here, which is the Allegheny State Park site. So if we pull those sites out and look at their relationship with the Randolph hatchery strain, this is a picture that Scott provided from some of the really unique looking brook trout that they find down there. Pretty shiny brook trout. But we found, in this site, we found a little bit more evidence of introgression. There's been a lot more stocking that's been occurring in the more recent history of some of those sites. We didn't find any individuals that were directly assigned to the Randolph strain, meaning no individuals were necessarily hatchery individuals that had been stocked, or they were not also offspring of hatchery by hatchery crosses. Most of these were, first generation or close to F1 hybrids potentially. So a little bit more introgression in some of these sites. So just want to summarize some of these results. Kind of looking at all of the patterns of diversity in the structure that we looked at across all of these sites. Really, and I think this is consistent with brook trout genetic findings in other locations. Brook trout populations are very genetically specific to the site. So diversity is partitioned across the watershed, but very specific to the site level. So there's a lot of genetic, we also, for these sites, we saw a large variation in diversity and how that was structured and partitioned across all the sites. Some sites were more variable than others, and more diverse than others, but a lot of the sites were on kind of the lower edge of those diversity estimates. All those sites also had all those pairwise estimates of FST, that scatter plot that I showed, all those were significantly different, meaning that all those populations were genetically distinct from each other. Even for genetic populations that were geographically close to each other, they could be still very genetically different, although in some cases they were a little bit more similar if gene flow was allowed to occur among those sites. If we group all the sites by watershed, I didn't talk about the AMOVA analysis, but when we look at an analysis of molecular variants, we found that really watershed structure didn't explain the primary source of that genetic variation. That genetic variation really was partitioned more on that sub-watershed or that site scale. So if you're more familiar with like some of the Eastern Brook Trout language, more that patch scale, or even sub-patch, potentially. And then if we look at, for those sites where we look at introgression with the Randolph fish hatchery, we found that introgression was really low in a lot of the sites that we looked at where stocking had previously occurred. And within the Allegheny State Park, some of those fish indicated introgression, some types of history of introgression. What does this mean for management? So there's a lot of information here that it's going to take us a while to really tease out, working with Scott and Pete and Fred and Betsy and Tom. There's a lot of points that we can pull out from the data. I think especially as we had basically double the number of samples. There were a few individuals I mentioned that we had resampled through the course of the sampling process. I think there were maybe about 5 individuals at the most. Scott was shaking his head. And what we found in a lot of those individuals, they were sampled initially in one site and then they were sampled again in another site. So they were able to actually document movement of some individuals from one site to another, so between watersheds, which was kind of interesting. It provides a lot of insight in terms of the potential for brook trout to move through some of these habitats we didn't think they potentially would, like through the Allegheny River during certain times of year. We can also use this information to look at connectivity among the watersheds and among these sub-watershed sites. So in terms of trying to identify areas that maybe focus restoration efforts on in terms of doing habitat evaluations or habitat improvements, or trying to focus the fish passage efforts on to kind of restore that gene flow potentially to help maybe boost diversity or the potential of those populations to be a little bit more resilient over time. At least for the Randolph hatchery that we looked at for that strain that was stocked in some of these locations, we didn't really see that past stocking had a big impact on the genetic diversity of a lot of these sites, which was really useful. I think there's a lot of, there was some kind of concern that perhaps that stocking efforts might have swamped out some of the local diversity. And we can also use this information on if restoration efforts is going to be done through maybe translocations from one site to maybe a neighboring site. We can use this information to help maybe potentially identify donor stocks that could be moved from one to another if the local population has become extirpated. So that's a potential use of the data. And really primarily, all this kind of ties together in terms of, we can use the estimates of diversity to really help identify populations that have low diversity that you might want to target some restoration effects on, and identify sites that are maybe at the greatest risk of local extirpation. So with that, we already talked about that. Have time for questions.